Welcome to this afternoon Forum 360. Really excited about this topic. It fits so well with the theme of SciTech this year. Think of boundless discovery. So the quantum revolution and what does that really mean for aerospace? I'll call myself quantum curious. I'm certainly not an expert. We've got the experts here to my left. And let them each introduce themselves, talk a little bit about what they do, what their company does, what their perspectives are in terms of this quantum revolution that we see ahead of us and how it could impact what we do, whether it's on the aviation side, space, all of aerospace. So maybe just a little bit about myself. You see my title there. I lead a flight and vehicle technology team. And again, we are all quantum curious. I have part of my team does all things aerodynamics, and computational fluid dynamics, of course, is a key to that. So we have this quantum thing somewhere on some distant roadmap. I asked the panelists earlier, what does it mean? Is it even a legitimate question to ask, what does it mean to have quantum at scale? But anyway, we'll defer that. But that's what we think from a CFD standpoint. I have another team that's all about guidance, navigation, control. Certainly on the nav side, quantum IMUs. We'll have some expertise here talking about that. But there's some real, I'll just say nearer term opportunities that those of us who are quantum curious can get our heads around. But there's such a range, a gamut of what the opportunity space here is. So anyway, very, very excited to introduce each of you. And we'll just go down the line and spend a little bit of time with each of you before we open this up to Q&A. Go ahead, Miriam.
Hello, everyone. I'm Miriam Newman, and I am a Chief Cloud and Data Architect on a program at Northrop Grumman. I'm a physicist by trade, and I think part of the important thing that I wanted to bring today is talking about how we integrate quantum technologies and future technologies, whether it's quantum AI, into aerospace. This is a really powerful place to have this discussion. I want to thank the team that put this together. This is a hard conversation to bring into a room. It takes work. It covers a wide landscape. And when we're here at SciTech, we all get to come together wearing one badge and really bringing academia, where they're shaping future thinkers and investing in fundamental research, to industry, where we're really understanding how technology behaves and will survive under real-world constraint, and then strategy and what we're actually going to decide to scale long-term. So one of the things that I work across systems software test, and one thing that's so powerful right now in looking at quantum mechanics is really obviously stating that we are looking at nonlinearity. And when we look at how we transition from linear, our decades past, and how we've evolved to a certain type of governance that runs a lot of our programs, it really defines how our programs, how we take a new technology and how it goes from demonstrating a concept to really surviving commitment and scale. And we talk a lot about how we accelerate innovation, and really what that means is accelerating understanding and ensuring that we are collapsing uncertainty in a way that we can measure and test and bring those technologies into the execution space. One of the things I know, it's kind of how does a physicist end up in cloud and data? Well, I started with first principles and continued to follow those problems. And one of the things is, as you move and you look at your TRL1, TRL6, and we look at success criteria, how do we mature those capabilities, right? We're in the lab, we're looking, we're characterizing them, we're building, we're demonstrating small concepts, small experiments. We're looking at how we measure timing, drift, uncertainty, looking at what the risk is. Does it have promise of becoming something more? Is there an application that's looking for, does this have an application space? And so as we bring that jump over, I have to look at really all data as a measurement. And I think that's really one of the things I wanted to bring to this conversation is some of the panelists here are doing a little bit more quantum specific research right now. But I want to discuss how we move from understanding the measurement and the success criteria from something up to a TRL6 into the application space where we are now talking about commitment and scale. And so what happens is, as you are looking at timing, you're looking at drift, you're understanding couplings, you're really working with uncertainty, how you bound the problem and how we use measurement for understanding how mature that capability is very different than when we bring it into the program environment. When it crosses that boundary, we do a handoff. It becomes a work breakdown structure. It becomes a control account. It becomes a network and planning package, right, with discrete tasks now, where the measurements we're starting to use look like EVMS, right? And some of these compliance and governance artifacts were from an earlier time where we did incredible engineering, but the problems were bounded. They were simpler. They did not have the same complexity as how we integrate now. We have digital transformation. We have agile. We are integrating faster and faster, and still we're using the same kind of compliance and success criteria. As we look forward, this is our moment right now. As we're having these discussions, as we're looking at even working with adjacent technologies and defining what the next 5, 10, 30 years looks like, this is our moment to really discuss how we look at success criteria and what the cost and affordability is to pull these new capabilities on at scale and when we're honoring commitments. So that is what I'm hoping to bring to the conversation today, and look forward to your questions.
Very good. Thank you. All right, Falgun, over to you.
Okay, great, thank you. Hello, everyone. So my name is Falgun Patel. I work at the Aerospace Corporation. I'm a general manager of their physical sciences laboratories. So let me just say a few words about who we are and what we do. So the Aerospace Corporation is a nonprofit, federally funded research and development center. And our job is essentially to help all manner of government, so from civil to the defense side that work in space programs, make sure that essentially all their missions are successful. And so this involves being there and present with our customers from start to finish, all the way to operations. And because I work in the physical science laboratories, part of our job is also to look ahead at what technologies might be necessary in the future or might be useful for certain missions. And so we have an effort in quantum technologies, and and I think as we'll go over later today, whether you want to look at it from a basic science perspective, applied R&D perspective, the engineering side, my interest is in all of that. And I also have let's just say that I'm more interested also in trying to understand how technology transitions. And so at many times, we'll also look at what is the actual business impact, or how would this scale into a business? How can you successfully, transition it? Because if you think about it from a TRL 9, right, every product, you don't think about all the core components in there. It just works. And so for quantum to get there, it might be a long road, but I think we're at the point where even if you look 5 years ago, a lot has changed. And even so, it's just the merging of many technologies. And I think we're at a cusp, as Miriam said. So.
Thank you.
Sure.
All right, Danny. I just have to say, not the the last but not the least of my frenemies on stage here, from Lockheed Martin. Go ahead, Danny.
Appreciate that. Hey everyone, my name is Danny Cougar, and I'm the quantum technologies lead for Lockheed Martin. So I do run a centralized quantum strategy for our business. Back in 2021, we inherited a new CTO from DARPA at the time, Steve Walker, and we really revolutionized the way we think about what we call 21st century technology strategy, and we organized our way around 14 different tech domains. Thankfully, quantum was invited to the adult table, and really the investments we've been doing since as early as 2008 turned into this technology domain, which has been a significant part of what has already been shared on stage, which is, an aerospace and defense prime's role in really understanding how do you develop quantum technologies that are going to impact the warfighter or impact our customers. And that's really where we've built our strategy, right? So we have investments in quantum navigation and timing, remote sensing and communications, and then of course quantum computing. And for each of those, we've really built our investment on the back of what is already a very impressive quantum ecosystem. We really do try to partner first, really realizing that there are almost 500 different quantum technology companies worldwide, and Lockheed Martin operates in almost all of the places that those quantum technologies companies exist. And really our role is to partner with them to bring engineering expertise to really realize what's already been mentioned, which is how do we pull these technologies out of the lab and demonstrate them in a very forward, capability-focused way so that we can really understand, hey, okay, this technology may be better in these types of environments. And then as quantum continues to mature over the next 10 and 15 years, there's going to be much broader applications for quantum technologies, but for sure within aerospace and defense, long history and lineage of really fine technologies being first demonstrated within our community and then first dispersed across broader markets. What I'll say is, we, and we'll talk a little bit about it here, is we've really seen an incredible amount of incubation at our company with our partners that are really now focused on demonstrating quantum technologies, reaching potentially TRL-6 and things like that over, the next 2 to 3 years across all these different portfolios. In our non-computational quantum investments, again, those are really focused and really much more near term. We do have an investment in quantum computing, but we are really, developing algorithms and defense-specific applications and partnering with those quantum computing companies. We're not building quantum computers at Lockheed Martin. But yeah, I can talk through sort of how we've gotten there and what we really think could be the most impactful for the warfighter, and hopefully also, I know there are a lot of customers here, how we can work with our customers to drive investments that are really focused on, again, how do we transition these things and have higher impact for capabilities that are needed and gaps that we've identified that we think quantum can help.
Excellent. So I'm excited to engage the audience here on questions. So reminder to post your own questions, but I have a handful of my own. And I'll start with you, Miriam. You mentioned nonlinearity. And there was an implication there around that thinking process that we need to perhaps train our leaders as well as engineering teams, maybe the supply base. Can you expand on that a little bit?
Sure. One of the things that I've noticed in getting educated early as a physicist is the ability to handle incomplete data sets and to handle uncertainty. And really what it becomes is not necessarily what is the method and am I trying to get to the answer, but what am I solving for? And so I find that as I'm leading teams across disciplines, a lot of times I arrive with a collapsed set of questions where we're already in a regime of nonlinear risk. Nobody's calling it that, but that's what it is. And I'm asking, what are we given? What can we measure? And where are we trying to go? And this is really the beginning of what I call steerability, where as we bring nonlinear technologies into the program space and we get to something like a PDR, we have to start understanding what the couplings are, and that has to happen in the lab. That has to happen with the engineering and scientists, where we have a new set of key performance indicators and things that we continue to monitor along with EV so that we can test assumptions as we go. And as we look at the students in universities today, one of the things I would highly recommend is that we have to get comfortable with uncertainty, failing fast and failing often, and being able to set up the problem when we're not exactly sure what we're solving for.
Oh, wow, that's very provocative. I deal a lot with uncertainty quantification when it comes to, concept development and our tool set supporting that. I have at least one PI probably presenting a paper right now on that, but I think we could learn so much from this whole field in terms of challenging our thinking, challenging, the paradigms around, engineering, we all love to have things that are deterministic.
Yes, we do. We do.
Maybe as humans we love to have, determinism, but no, that's really provocative. Any other comments on that, whether it's in the workforce or our approach to design?
Well, I think, quantum tends to evoke in people like this mystery, right? That I'm like, oh, wait, you're way too smart. I don't need to, that's above my head. But if you really think about it from just a pure technologies perspective, this is like any other period in the past where some new technology has come forth, rising from basic science, let's just say. And, it takes time to understand and for it to get into the college curricula and for, products to come about and mature, right? And so I think to some degree, yeah, sure, there is a mystery around quantum physics and quantum technologies just because I think we're not used to understanding it. But once the technology is used in the product space, right, you have actual hardware, you're not going to think about the quantumness of what's behind it, right? So, and as we talked about in the green room, right, we all use laser pointers and laser technologies embedded inside many of our lives, right? And whether it's in various fields, manufacturing, medical, just industrial, anything. A lot of these products, lasers are quantum-based devices, right? But nobody's really they just push a button, it turns on, and they're good to go, right? So I think right now, I think Miriam is correct. We just, quantum, there will be uncertainty around the product development, around the understanding of it, et cetera, but I think we've lived through this already in the sense of new technologies coming forth, and then how do we fold it into our everyday lives and mature. So
I have a follow-on question for you, but I'll pause a little bit.
I'll just pull on the workforce thread. I think across obviously aerospace generally, but at Lockheed Martin we've recognized that we have 60,000 engineers. There aren't enough physicists or PhDs for me to hire to execute the work that's coming in quantum. So we really focused on how do you upskill your engineers. And I'm actually not a physicist, I'm an engineer. I came into quantum early in my career, but I have to give Lockheed Martin a lot of credit for putting an engineer in front of a pretty hard science portfolio. And I think that was really representative of where the field is. And so we started a quantum talent pipeline. It's a yearly program where we're focused on choosing, Lockheed Martin engineers to work with our quantum SMEs to really upskill and become more quantum ready, right? These folks likely aren't going to perform on our quantum programs tomorrow, but they're definitely going to be in a better position that when quantum does arrive to their desk, they're going to be able to understand how to do it. And then on top of that, we run a yearly seedling challenge where we give Lockheed Martin engineers an opportunity to say, I know a little bit about quantum, but I'm an expert in machine learning, or I'm an expert in CFD, or I'm an expert in phenomenologies. I think I'd like to explore how quantum could help me solve some of my hardest problems. So, one of the papers we put out just last year was around using quantum computing as a way to really understand different types of phenomenologies in quantum chemistry and kind of putting us, again, I'm not claiming quantum advantage, but there's a better understood path at Lockheed Martin to the way we may solve different phenomenologies for some of our products in space using hybrid quantum classical computing. And that, again, all the things that we talk about in quantum are awesome. None of it's going to come to realization unless we have a workforce that's ready to actually use those technologies and leverage that for solving some of the problems that just you can't do conventionally today.
Thank you. Falcon, back to you. You said something around scalability and metrics. What do you think are those kind of key success factors or other metrics, beyond that typical TRL that we would need to assess in terms of readiness to really, I'll just say, go quantum at scale, whatever that means?
Sure. So I can offer some insights, but I think Miriam can also add to this as Danny. So I think depending on the particular category, right? So I tend to think of when you're bringing technology to scale, or you're transitioning from one TRL to another, NASA has a nice definition of TRL, but then it can also become subjective, that I say I'm TRL 6, but you say I'm TRL 3. How come we can't meet in the middle, right? And my funding's riding on it, right? So it's really about, again, just, I tend to look at it like if you really want to scale and you want to get more people interested in your work, you really have to get back down to what is a problem that you're solving, and can you explain what your idea, what your product is actually doing to help solve the problem. If you're having to go deep into the quantum physics, right, I think you've kind of failed a little bit. And so I think like whatever technologies we're developing, whether it's a novel sensor, right, that's based on a magnetometer, people will compare it, your first customers will compare it to magnetometers they can buy today. And so, first you have to get them to understand that the quantum version of it is actually better than what they can procure today. And then the scale argument comes in where, again, you bring in the workforce that are the engineers that, that can take your idea and say that, hey, we know how to make 10 of these, 100 of these, and then just kind of build out from there. And I think it becomes more of a traditional engineering challenge from there once you get past the understanding. So to me, the success metrics are really just around the business side, just like they're always around. You always need to be able to explain what problem are you solving, and how is this better than the incumbent technologies.
Thank you.
Yeah, I'll add a little bit. I think with scalability and success criteria, as we move through the maturation of any technology, scalability means that we understand that the assumptions that we are making are going to hold as it hits real world constraints. And as we've gone and we're doing continuous integration, that is an excellent way that as we're able to carry the timing, the drift, the couplings, real engineering data variables that you are measuring in the lab, that's how you start to carry it forward for scalability when it's along your cost vector. Another thing that you mentioned was, I think that, excuse me, when we have, when we're moving, we're looking at success criteria, there are a lot of frameworks that we use when we're talking about commitment, because right now there's consequence, right? I think one of the things is technology, when it no longer becomes a research problem and it's touching the mission, learning becomes very important because now we're talking about consequences outside the lab. But even within the lab, if we use the same frameworks to manage that, the success criteria, you still have a budget, you have something you're solving for, you have labor, you have material costs, and you can manage that program the same way you would a large acquisition program. And you can start to see where your uncertainty is hiding, which is where your risk really is. And that's where you have workarounds that eventually add to your cost, right? If we start to look at where teams are using tribal knowledge, superstition, rapid prototyping, versus systematic rigor, you start to see it in pockets. Now, in the earlier phases, IRAD is really where we want to do rapid prototyping. You're going to have a small, lean team. They're there to demonstrate the concept. They want to start showing promise with very specific algorithms, equations. They're solving for something specific. And then as it starts to merge and morph into an application space, and we get into a more mature capability, that's where we kind of have to compare where that risk is hiding and how much we can actually prove that we can manage uncertainty as the capability matures. And that's using all of the data that you have, right? That's how long something's taking you. That's if you can estimate it, and how many people it takes to solve it. What are those skill sets? However it looks, when you scale it, it's not going to be that much different.
Thank you. That begs a question I'll pose to Danny first. So what technologies do you think are the most ready for true operational use or deployment?
Yeah, I mean, quantum sensing for the means of navigating or sensing very faint, sometimes undetectable types of things is going to be the, sort of the first thing that quantum is going to, show that there's a place to help. I'm by no means saying quantum sensors are going to replace conventional sensors for navigating in things like GPS at night environments. But what's really important is to know that quantum is another technology that when integrated or fused or properly following engineering disciplines to say, hey, now there is another capability on board that when I'm faced with an intractable scenario, I can click it on. And so, there's quite a bit of open research, and then obviously the United States and other sovereign countries have invested in, things like the DIU Transition for Quantum Sensors program, in which we're a performer, so is Northrop, and really focused on how do you take, known quantum sensors like atom interferometers, inertial sensors that we can then create, a pathway to building a full IMU. And then there's been announcements that some of those have even already been deployed and put on, different vehicles to really understand what those capabilities will be. And, and quantum inertial sensors are really focused on, tackling the drift problem, right? There's an inherent amount of error accumulation when you go out and deploy some of these sensors, for long periods of time. And yeah, we think that quantum, specifically quantum inertial sensors will play a very vital role in navigating in environments that are highly contested or are very, subject to those types of drift and error. And then, there's a whole other suite of quantum sensors like magnetometers, gravimeters, these gravity-aided sensors that will provide some level of advantage when trying to navigate or sense different objects. What's really interesting, though, and I'll just say this because it's one of the hills I'll die on, is that currently, at least in the U.S., there is the investment in quantum computing versus quantum sensitivity is not at parity, with the reality of which is what's going to transition first.
Oh, that's interesting.
So what's going to transition first is going to be sensors, right? That's, I think generally in the quantum community, everyone agrees on that. I'm a huge quantum computing person. That's where my research started, so I don't want to poo-poo on quantum compute, but it is further out as far as general applicability and transition opportunities. But to date, the U.S. has invested about 80% in quantum computing versus about 20% in quantum sensing and other non-computational quantum technologies. And I guess, I would say the answer to that question is the technologists and a lot of the folks within the quantum community agree those are the realities, and it would really be great if, at least in the U.S., we can start to create a little more parity in those investments so that we can, again, the focus is to get capability in the hands of our customers. And that's a path where I think, there's a lot of really intriguing demonstrations that have happened just in the last year and that are going to be coming up in the next couple of years from a lot of the folks on the stage. And I think everyone's excited to see those. And those are all going to be in sensing, navigation, timing, comms, things like that.
Well, those of us in the technology business, the R&D business, we're faced with that, valley of death, and getting over that hurdle to true operational capability goes well beyond the TRL. There's the illities that we've discussed in past forums. There's the supply base that we don't talk about too much. What do you think about the supply base when it comes to, again, I'm just picking on your example around sensors really being first, and that's open for broad comment here.
You go first, yeah.
Yeah, I think on the sensing side, the supply base is, I guess, generally better than others. I think, when you think about, let's just say, I think a small lab could put together a sensing portfolio if they wanted to, right? That lasers and light sources are, tend to be available. If you think about, if you can design around a nitrogen vacancy diamond thin film, they're generally readily available. So while I won't say that the supply base is robust, I think, you don't need to have the investment capability of a Google or IBM to work on a quantum technology if you're focused on the sensing side, right? So I think, and so for the entrepreneurs in the room, right, I think if you're thinking of getting into these areas, I think on the sensing side, I think Danny is correct. I think those areas do offer not like a near-term ROI, but they do offer, say, a faster to market type of option. So.
Thank you.
I'll just tag on to that. I think the part of the opportunity there is the integration of the capability and what that application is and how it ties into the digital ecosystem to make it easy to monitor and actually use that application.
Yeah, and I'll just say that I'm not, again, I don't want to claim that, tomorrow you're going to see some sort of article that says like quantum made it, but I think what's really important to know is that we're on the crux of the reality is in a lot of these technologies, there's more engineering problems to solve than physics problems to solve. And the reality is, though, if we do reach that day, which we call in the community quantum advantage, the idea that you've demonstrated that something quantum can do something that classically or conventional technology cannot. If we get to that day, my biggest fear about the supply chain is we will not be able to scale, because a lot of these companies, the quantum companies or universities or our industry, we're very set up for building those prototypes and getting to those like TRL-6 big meaty demonstrations. But if we get there and then some customer walks up to you and says, I want 50,000 of those, that is going to be a challenge where the current supply chain fits today. And I think folks like us who have a lot of experience in developing technologies at scale, manufacturing at scale, those are the types of questions we really need to start, and again, I want to recognize the US customers have recognized this as well, is like, how do we go then build not just a couple of those lasers, but dozens, if not hundreds, or different core components within the quantum ecosystem that are going to be necessary to scale. I don't want to say that's necessarily something we have to deal with in 2026, but I will say if we don't, as a community, start to really focus on building these different quantum, non-computational quantum technology companies through that mind, it might be challenging in the future. I will say the great thing about quantum computing, quantum sensing, quantum comms, whatever your company is investing, there's a foundational basis of quantum components that are necessary for all those things. All the investment in quantum computing 100% has impacted how quantum sensing companies have been able to bring their technologies to bear. So I don't want to say like one investment doesn't help the other, because it definitely does. Neutral-based atom or neutral-based quantum computing very much has impacted the way that we are now building atom interferometers and things like that. So again, one plays into the other. It's just really how do we make sure that the manufacturing capability is there when we do reach quantum advantage.
No, thank you. So I'm not sure whether it's my app or I'm just, everyone's listening so intently, we're not getting questions, but excellent. Apparently we are. I still have a list of great questions here. My last question, maybe, if you look out maybe a 5 to 10 year time frame, of course in this area it seems like things could happen very rapidly depending on investment. What should the aerospace industry prioritize? More test bed, flight demos, or other demos? Are there some qualification standards or shifts that we should be thinking about?
You go.
Okay. I have a couple thoughts on that. I would say that we have parallel pathways. So I didn't mention this at the start, but I'm an accelerator physicist by training, so I have worked at large injector complexes where we produce particle beam. And so in my mind, I can visualize as we have different technologies coming to a platform that have to meet milestones and airworthiness and certification, how we basically mature those in parallel pathways, and again use first principles where we know exactly what we're measuring. We start to incorporate one system at a time. We can show durability, repeatability, and it's not part of schedule yet. I fear that sometimes as we jump right to these big demos, we have a demo, but we haven't really proved that we can control the technology to an IMS yet. And that's a real subtle difference, that as we show demonstrations in that parallel process where we know it's going to be compatible with the data ecosystem, and we can start to bring it into the labs, and we can look at our modeling and sim and our theoretical framework, it allows us to bring it on board a lot faster with fewer surprises once we are doing some of those big demos on a real acquisition program.
Okay, very good, thanks.
Yeah, so I think for the next 5-10 years, to really accelerate development and where to focus, I tend to think let's just use the sensing as the thought model here. That for companies like us, where if we wanted to prototype certain technologies, I think you really need to have that side by side. What is it that you're comparing to? And for for the larger companies that may end up actually integrating a lot of these technologies in, you know, if they have standardized ICDs, right, that say, look, this is how we test or utilize the existing types of sensors, and we're happy to have a program that prototypes, so just, you know, get a line, right? We'll just get a line. We'll just start prototyping them together. But that's a good way to accelerate when, again, you can actually standardize on whether it's the ICD platform for actually testing and validating, and then also giving a pathway for smaller companies to come to the larger companies as customers, and then, you know, we can all probably compete for like who has the most bureaucratic contracting mechanisms, right? But again, these things do matter, and if there are ways to minimize some of that, where you can just, small companies can come to the larger companies, and then I think that has a beneficial impact across the supply chain as well. But I think, again, to Miriam's point, you have to standardize on how you're testing, so the scheduling, the budget, and all that kind of stuff. It all has to align, and the resources have to be in place.
Very good. Thanks.
Yeah, I mean, 100% agree. And that is really, you know, what's proven to me since taking over the portfolio at Lockheed Martin is like, that's our role as an aerospace community, is that there's such a long history of our companies delivering products. You know, these quantum companies are incredible, and they are focused on, you know, developing these exquisite, novel technologies, but partnering with folks like us, really, it shouldn't be their responsibility to bear that entire burden of that full product life cycle. And so really, you know, bringing our experience to those partnerships has been crucial in really seeing the acceleration. So I totally agree, in the next 5 to 10 years, more companies that have, you know, like engineering principles. I mean, the quantum systems engineer is going to be one of the biggest parts of this ecosystem in the next 5 to 10 years. And those are going to be the folks who maybe never even, you know, could spell quantum before when they joined a Lockheed Martin or, you know, one of the companies on stage. And really, those are going to be the folks who are going to be building the devices. So really, how do you think of this through, you know, electrical engineers, mechanical, optomechanics, all those things? That's really what's going to help accelerate us, and that's really going to be, you know, aerospace and defenses and you know, generally speaking, large industries' role in quantum. And I would say the quantum companies today, almost all of them are so receptive to that relationship, because it lets them really focus on, you know, developing the quantum technologies with a partner to then generate a system, right? To generate something that can be tested. And we've seen that through a few of our partnerships, to bringing technologies in, testing them in facilities, again, that we already had, because we're already developing the counterpart technology today. So yeah, I think in the next 5 to 10 years, engineering is going to play such a crucial role to accelerating these technologies to the field.
Can I add something? I think you made a really great point too, because we're building airplanes, and we don't always necessarily have the investment or the workforce to do the entire thing and develop all of the new fundamental science with the capabilities. So being able to pair and integrate allows us to still continue to accelerate on an actual platform. So I think that's an excellent point.
Yeah, we all agree, which is really lovely.
It is lovely, and so does the audience. So, you know, there are several questions around, you know, what's your guidance on pursuing a career in quantum, or at least getting your quantum curiosity satisfied with just enough so that you can actually talk to someone like each of you. You know, what would you recommend to an aspiring early career engineer or student in terms of maybe the first steps?
I mean, I can start.
Please.
So I'll focus on just the aspirational value, right? So if you're a student, or you're an undergrad, you're going to grad school, or you're trying to specialize, you know, my advice here would just really be that, you know, I think at your level, when you're starting to enter into a company, I think probably the more common criteria that people will be looking for is just are you curious and are you multidisciplinary, right? I mean, that it doesn't mean you have to have 5 like degrees, it's just more that if you're starting off as an electrical engineer, but you have this interest in quantum, but that you can actually not only design, but get in the lab and actually, test and solder and, just do more things, right? I think like more and more we talk about specialization, but I think especially in small companies and in a growing field, you have to be able to wear many hats. So you don't want to go in and just say, look, I do software and that's it. And my passion is, just this one thing, and I don't want to expand it to others. I mean, you'll find in your career that after 4 or 5 years, you'll become an expert in whatever project you're working on, but you'll want to transition. Doesn't mean you need to change jobs. It just may mean that you might want to take on more of the product aspect of it or a bigger program. You might want to lead a team. So you have to be receptive and curious. And obviously just, you should just be a nice person too, I think. But yeah.
Nice people are good. Yeah, in quantum, I think like in 2026, right, there are an incredible amount of opportunities across academia, industries, ALA, other types of things like that, where folks can get, on their own time or as a part of their curriculum, get sort of an introduction to quantum. And I will also say now more than ever, there are so many quantum companies that have put, especially in computing, put their capabilities as open source. In IBM, who's a partner of Lockheed Martin, you can go out and you can get, a certain amount of hours to program on a quantum simulator or actually quantum hardware. And I'll say anytime I get a resume and there's even a mention of some sort of quantum, ready or quantum course or something, I'm like, well, then you were thinking the right way, right? It's not like I'm not looking for experts in quantum. I'm looking for engineers, like you said, that are curious enough to say, you know what, I know this thing's coming. I need to look into, I need to do some education. What I will say generally then in the ecosystem and kind of what's going to happen the next 5 or 10 years in quantum is you, as a person coming into this space, you need to know what type of company you want to work on quantum at, because working at my company in quantum is much different than working at a quantum technologies company. And it's we happily share talent across the quantum ecosystem in aerospace. But the reality is the folks that come work for my group versus working for a quantum technology group is we're working on a much broader set of applications and a much broader ecosystem of things that we're trying to challenge versus a quantum company that, a lot more people in the lab. There are engineers there, but they're really focused on 1 or 2 types of quantum technologies. So I always say, like, go educate yourself. There's so many opportunities, way more than there ever were when we were in school. Linear algebra, absolutely take that course. And then I would say, really try to understand what type of company you want to work at, because working in quantum looks very different depending on the type of company you're working at.
Thank you. How do you view the intersection of quantum, maybe everything, but I think the question was really about quantum computing and AI and machine learning. Anyone want to jump in on that?
I can jump right in. My comments here are back to sort of the things that we've mentioned. A lot of technologies today solve really hard problems really, really well. So when you think about something like quantum, which still does have, a time to transition, right? We don't have all of this in our hands every day. Is you have to say, what is, like Miriam said, what's the cost of using a AI-based system versus using potentially like a hybrid quantum classical AI system? And that's going to be a tough road for quantum, for at least on the compute side. I mean, a lot of these quantum companies are sort of using 2029, 2030 as the date that there will be, relevant quantum computers for generally, applicable problems. What I mean by that is like quantum computers that potentially could do something classical technologies cannot. But AI, we're learning a lot. I would say the best thing that's happened for quantum computing and AI is that they're pushing each other. If quantum computing companies come out with a result that's quite provocative, the AI community, and I say the conventional high-performance computing community, immediately say, well, no, we can already do that. We do that very well. So if anything, they're pushing each other. I will say the phrase quantum AI scares me a little bit because the reality is where we need to be is each company needs to have an opportunity that every engineer has access to a CPU, GPU, and QPU. And then based on what the problem they're solving,
Yes.
they can choose which one they need to use or a combination of the two. And as long as we have environments that can support that reality, then we'll be there. But quantum and AI, like together in one sentence, is not a thing.
I like that vision.
I was going to just add to that. Regardless, quantum AI, the most important thing we can do is understand and use the data that we have. AI is going to amplify any assumptions that we give it. If our assumptions don't hold, it's not going to give us the answer that we're expecting. We're not going to get the value that we are expecting. So making sure that we are really focused, especially in this industry, on how we use tools and automation and understand our data, and that the understanding and that learning is accelerating that maturity and capability, we will be able to have more certainty as we come to apply it, and that will feed into our total life cycle cost.
Okay. Cool.
Let me bridge the last question and this question. So I think like if you're thinking of entering into the quantum technologies like a ecosystem, right, at a job, and quantum computing is something where you're thinking of going into. My thought here is that, you know, if you just look at the rapid advancement of like AI tools, right? But just keep in mind that yes, we all can access the big company tools, the Googles and others. But I think like having it completely embedded in our lives is not quite there yet, right? So if you've ever tried to use like chatbots and other things from smaller companies, right? They're not really there. But from a quantum computing perspective, you know, I think bear in mind that I don't think like we're quite as mature at trying to take a classical problem and then converting it to say, how would it actually be projected onto a quantum computing platform? I think people focus so much on the very basics of these are the qubits or this is the algorithm, but the algorithm is probably hard for most of us to understand, let's just say, right, unless you're really deep into it. So I think if you want to try to get into the space, but you want to focus on just how do I really understand what problem is being solved, and then let me just take a look at the quantum computing platform where, again, there are freely available resources, and just saying, how would I translate this, and really get a good understanding of that. In my mind, I think this is like the early days of computers when not many people understood how to program a computer, but those that invested in early, you know, it paid off for them, but they evolved with the times. And so if you want to join the workspace, right, and you want to think about the computing side as your area, I think this is an area that isn't quite, let's just say, mature, right? That people, you know, aren't looking at how to actually project the problem onto a computing platform.
Hey, quick question, and then we'll do maybe a little last, hey, you know, what is the thing that excites you the most about this area? So the quick one is, are there existing consortia or industry working groups? You know, we've discussed a wide range of topics from, you know, how does someone get into this field, the supply base, what's that future state look like, but it seems that, like it begs for some forum beyond this.
So there are a lot, IEEE and APS, so there are a lot of other professional societies, and even just your engineering societies that will also have additional technical committees that put out quantum publications, and I'm a member of several other societies, and I get a lot of updated research that's going on across academia and labs for quantum.
Yeah, I agree. There are other societies, and in terms of consortia, there are many, and you know, I think if anything, you probably have too many choices so you have to really do your work to figure out which one is better for you, you know, if you want to, you know, get involved.
Yeah, I'll just add that the National Quantum Initiative that was signed back in 2017 by the United States government, which is currently within reauthorization, funds something called the Quantum Economic Development Consortium. I'll caveat this by saying I am on the steering committee, so this is a little self-serving, but The Quantum Economic Development Consortium is made up of companies, academia, and really just players within the quantum space to say, how are we bringing together organizations, as well as there's a huge focus on workforce, use cases, national security, all these different parts of the consortium that really, again, are independently looking at what is that pathway for, adopting quantum technologies at scale. All these professional societies are obviously, APS March meeting is like the place to be in March when it comes to quantum. But there are a lot of really lovely conferences and opportunities. And then at universities as well, I mean, there are like every week it seems like I'm introduced to a new like student quantum group, and I'm like, this is so good. There's a quantum engineering groups now, all these things where, there's definitely ways to get involved. But if you're in industry and you're not a part of QEDC, it's definitely a place where, again, it's run in an independent way to really understand everyone's role in this community going forward.
Excellent. So, okay, the last question, and this was the most upvoted. Which specific problem are you most excited to see quantum science potentially solve? And I'll just add on that, maybe it's not a specific problem. What's the area you're most excited about?
It's hard to choose just one.
Come on, Falcon, you're close.
So I think I still gravitate towards the sensing side. I think so the reason is this, that I think to me, a mark of like a good technology is something that's just there and we don't even know it, right? Like it's just improving our lives, but we're not, like if you really dig down, you'll know it's there, right? And this is pervasive in everything we do. And so sensing is definitely there. And my view, from an excitement perspective, I would say that like when you have quantum sensors that, again, from a quantum advantage perspective, that they offer slightly better or profoundly better, let's just say measurements, right, compared to incumbent technologies, that they start to become pervasive, and then all of a sudden, whether it's medical or computational or just like the understanding of our environment, and it's getting into our cars or it's getting into space, right? It just becomes a part of us. And I think like then, computing is very far off and people, they may not have a direct link to it, but I think sensing is something that people have more connection to. And, being in the field, I would like to see that come up.
Thank you.
First.
Okay, Danny.
Yeah, it might sound like a cop-out, but I think one of the most exciting things that quantum might address are actually the things that we have no idea need to be addressed, right? I mean, when the transistor and other types of computing over the last 50 years has come about, we're solving problems today that we never even identified as a thing we needed to solve. So whether you're looking at sensing or computing, the reality is when these things are finally in our hands, these quantum black boxes are going to probably give us abilities to solve things that we didn't even identify in 2026 that needed to be solved, which is sort of a little bit of opposite of what I've been preaching, which is we really need to focus on things that need to be solved so quantum can transition. But specifically in computing, we always kind of bucket ourselves into machine learning, optimization, and things like in chemistry. And then people are like, oh, what's going to be the first big win? Well, in conventional computing, the Excel spreadsheet was the first big win. I don't think anyone would have guessed that would have been the killer app. So I always say chemistry is going to be the first thing that quantum computing solves, and that's extremely exciting for folks in that industry. But the reality is it's likely going to just show up all these other things that we didn't even think were available to us now that we have quantum technologies in hand. So it's a bit of a cop-out because it's not specific, but to say that this is such a revolutionary technology that once we have advantage in this area, there are going to be questions that we get to solve we didn't even know to ask.
Excellent. Miriam.
So I'm reflecting on some of the comments made today, and I think as we look at some of these new technologies, they're exciting, right? Anything that's new, that's novel, that's different, we gravitate towards. But there is something to be said for, does that technology make life easier? Does it solve a problem that classical, cheaper methods don't solve? And so when I think about, and I might be a little less specific here too, but when I think about quantum sensing, quantum optimization, or even new materials, and I look at the aerospace industry maybe 25, 30 years from now, how we manage fleets, how we handle nav and timing, I think it's actually really going to give us an edge. And so I think that that is very, very exciting overall for the additional things that we will be able to do as it makes fleet management and life cycle more affordable. So I think that's very exciting.
Okay. Well, we actually have 5 minutes left, so now that you answered that last challenge question from the audience, any parting thoughts, or maybe it's a challenge to the team to go visit something in the expo hall, anything that you would like to share? And I'll start with you, Danny.
It's an exciting time. I'm very privileged. I get to work on quantum 100% of my day, and 16 years ago when I started at Lockheed Martin, I would have never imagined that as an engineer, but I think it's really reflective of what's been happening. The investments in this area are huge, right? I mean, everyone reads the popular press, and billions and billions of dollars have been putting into private and public quantum companies, and that's very exciting for everything we're doing. But in order to pull that thread to where we're actually getting to test and deploy and use these systems at scale, it's going to be a very interesting ride. So just continue to really track the quantum revolution closely, but do fact check, do your own work, hire engineers that are interested in trying to challenge some of these claims, and really focus on how is quantum going to address things that can actually be done, but not necessarily. Again, there's just a lot of hype out there, so just keep following it closely, but do work with your team to always try to validate those results, so that we, there's not a quantum winter coming, but we really want to make sure we're realistic about how quantum's going to.
Oh, that's an important statement.
Yeah.
Yeah, I think there was a question in there about the hype. How do we combat that? I think you hit on that really well. Falcon, what are your parting words of wisdom?
So I'll separate into two. So for those that are just about to enter the workforce, right? So if you're just starting out and you want to get into this area, I would say one thing that's very different for you than say it was for me back when I was finishing is that you have a wealth of resources at your fingertips. And so even if you don't have direct connections with companies, whether it's quantum computing platforms, I mean, you can play around with the emulators and get some general hands-on experience. I think that automatically puts you above average when you're going to talk to people. So just try and utilize the resources, try to understand what you can. You don't need to be an expert, but if the fact that you've tried and that you've kind of committed to understanding aspects of whatever quantum area you want to learn, that's good. Second part is more about the companies, and if you join a young company, or or you're an entrepreneur, you want to start a company, or just bear in mind that around the hype idea, right? That it's easy to just get very focused on your own area and your own bubble. But just remember that at the end of the day, it's a business, and so what will actually benefit you is if you can explain to your potential customers why and this is not a profound statement, right? But why your product that includes quantum tech is better than the incumbent technology, and provide a vision for the future. I think that's good, right? So to be able to actually clarify that in a concise way is good. So that's my parting thoughts.
Very good. Miriam.
I would say for some of the students and engineers entering the workforce, or graduate students, take the time to do some research or get into a lab outside of your lab assigned with your regular class, because when you are operating under real world constraints and you have to figure it out, that's where you really start to improve your first principle and your rigor and how to handle uncertainty. And from there, there's so many ramps to onboard. Companies have so many opportunities. And I think here, if you have the, your foundations, which Everybody coming out of university has incredible, math skills and problem-solving skills, programming. You're introduced to data. There's so many ramps to onboard, and what you do in your first 5 years of your career will probably be different than your 5 to 10, and different beyond that. So keep learning, get comfortable being uncomfortable, and put yourself out there. And that's what I would say is some important advice.
Very good. Thank you. I tell you, this panel has been, truly informative for me personally, and hopefully for all of you in the audience. There's a lot of thought-provoking, more than nuggets that you shared today. So thank you so much, and let's give all of our panelists a round of applause here. Thank you.